For decades, power system planning was very predictable. Demand grew gradually, generation was centralised, and power flowed simply from large plants to customers. Today, that model is over. Planners must account for massive renewables, storage, electrification, and huge data centres. The grid is now bi-directional, weather-dependent and constrained. The key question is now, what is the most efficient investment plan to prepare your grid for the future? And answering it requires balancing many variables: generation, transmission, flexibility, costs, and policy. Representing all of this with traditional models is complex and computationally impractical. VeraGrid's integrated planning workflow supports this process by connecting the grid model, multiple scenarios, investments, simulations, and results in one single environment. Let us show you how.
In this walkthrough, we'll focus on one integrated planning use case: identifying grid investment options for a future load growth scenario. The output of this analysis is a Pareto front of investment plans. Each point represents one possible expansion plan, combining different investments evaluated in VeraGrid. Here, we compare investment cost against the technical performance. The technical performance can include many criteria, notably adequacy and static and dynamic analysis metrics. In this walkthrough, we focus on voltage violations, line overloads, and line losses. The Pareto front helps us to filter out weak plans, those that cost more while performing worse. The remaining plans show the key trade-offs available to planners. This gives the planning team a clear set of options without forcing a final decision too early. Now, let's start with the base system and see how VeraGrid gets us here. The first step is to load the grid model. In most planning studies, the starting point is an existing network model. The model may come from commercial power system software, open source tools, internal databases, or consultant studies and standard formats. VeraGrid is designed to work in this mixed environment. Once loaded, the model can be inspected and validated before planning decisions are tested. This step is important because the quality of the investment results depends on the quality of the base network representation. Now that our model is validated, the next step is to include coordinates. In VeraGrid, we can work both with schematics or directly on maps, which can be very useful in planning to identify non-electrical criteria, which is very key to the decision process. To do this, we load the coordinates from an external Excel and automatically match coordinates to the bus ID. We can then create a new map with all the substations and lines in the model. If we run any studies, this map will then color with the study results for easy visualization of what is occurring in the grid. Next, we should also add technology and fuel associations to the generators in the grid. For the fuel, we also parameterize fuel prices, which will be fed directly to the OPF. As the data entry process can be tedious in larger models, we have an integrated scripting tab. In this example, we're creating a script to automatically define the technologies and fuels, along with the associated generators, based on the grid case definition. The final step to set up the model is to import renewable profiles for renewable generators, and profiles for load active and reactive power. We do this by using the import wizard VeraGrid provides, which has an automatic profile assignment. We can then visualize the imported profiles using the graphing functionality. Now that the model is parametrized, we are ready to run studies. Since this is a large model with many time steps, it can be advantageous to cluster time series steps together to reduce the simulation time. In this case, we choose 400 samples to provide representation of the full year. We can then run an OPF and power flow over this cluster time series to obtain profiles for the full year. The results of these analyses can then be simply visualized both as a time series result and as a cumulative density function to identify overload percentages. We're now ready to create our scenario. Let's imagine, for example, that we expect load to grow by 5% in the upcoming year. We define this as a new scenario from our base model. We can then easily multiply all or selected load profiles by the expected growth. Let's cluster our time series again now, and run the OPF and power flow. With these results, we can identify which branches are suffering from overloads, and we can use these branches as a base for the potential new investments. We can once again take advantage of the scripting tab to take results from the power flow, identify which branches are overloaded, and create equivalent investments for each of these overloaded branches. We can then see that many new lines have been created, which are all deactivated in the model, and that when we go to the investment groups, all of these new lines and transformers are attached to a different investment group. Once our investments are all created, we can run the investment analysis using the time series power flow to obtain investments that will be resilient to the full range of operating conditions over the year. And with that, we're back to the start. we can now visualize our Pareto of optimal investments, and we can even visualize the reports that show which combinations of investments have been selected and what score they received for each of the different criteria.